This is a lesson on composition with rational functions in a precalculus course. In a previous lesson, I had talked about composition of functions, and I had originally introduced it with linear functions, but now we've moved through our arsenal of functions here, our toolkit functions, and now we're looking at rational functions. You should be able to proficiently and accurately do all these operations, these basic mathematical operations, okay, on the when you compose functions. So I drew up a couple of examples here for us to go over. I see students struggle with them because I think mostly because of the algebra. There's some algebra involved. It says fully simplify, and you can't just like take these two, add them together, and enter that in the computer. You have to fully simplify the solution. This also says find the domain as well, and I know students can sometimes struggle with finding the domain. The domain here, what I'm going to note, the domain here is determined again by the denominator of our two functions. So right away, I'm going to note that 2x plus 5 cannot equal 0. And I'm going to factor this down here. There must be a 2x here. There must be a plus 5 here and an x minus 1 here. Does that work out? 5 and 2 and plus 5 and minus 2. Yeah. So I also get x minus 1 cannot equal 0. So our domain is going to be limited by our original functions, which those to me are similar to extraneous solutions. So in a previous lesson, I had talked about extraneous solutions. So I'm going to say x cannot equal negative 5 halves and x cannot equal 1. So when it asks for like what is the domain, we're going to keep these values in mind. When we look at rational functions, there's going to be an asymptote there, and we won't have a domain, an allowed domain there, and we have to take that into account when we're writing that out. So let's go ahead and add our two functions, 2x over 2x plus 5. I'm going to note that when I add two things, I'm going to want a common denominator. This one has a denominator of 2x plus 5 times x minus 1. I can leave the 17x plus 25 here, but in order to get a common denominator, I need to multiply an x minus 1 here and an x minus 1 on top. Okay, so when I get this common denominator and then I'm adding them up, I'm going to distribute this here. So 2x squared minus 2x plus 17x plus 25 over 2x plus 5 times x minus 1. Okay, I'm not done simplifying yet. This is your algebra skills. Keep simplifying, keep simplifying. So I get a 2x squared plus 15x plus 25 over 2x plus 5 times x minus 1. All right. You can play your games, all the typical strategies for factoring that. I guess this because I'm I've known this material for a long time. If this is a book problem, a lot of times they'll make it like you need to keep simplifying, and I'm going to guess one of the factors in here is a 2x plus 5. That was just a guess. So I'm going to guess that numerator has a factor of 2x plus 5. In order to result into that, I need a 5 here, and then I think that can be an x, and then I need a plus sign here. So you can multiply that through, FOIL it through to make sure it backtracks to check your answer. And what I see is that this simplifies down to just this linear term over this linear term. That's going to be that. F plus G equals that. That's the simplified term, okay? And then when it asks for the domain, I'm going to go back up here. The domain is determined by these, but I would also check this here. But I'm going to note that that denominator yields the same unallowed value that I had already determined in the beginning. So when I look at the domain, I'm going to note that the domain can be any number except what can't be in that denominator. So it can be any number from negative infinity all the way up to negative 5 halves. Then it can be any number between negative 5 halves and 1. And then it can be any number from 1 up to infinity. So this is going to be the domain. right? All of that. It can be any. You can check the graph. I think it would be good for you to check the graph. I did not check the graph on this one. I'm allowing you all to explore that. I know that that's a tool you can use. What I wanted to show you is how to do this algebraically. How do you do this algebraically and make sure you're sharp on those skills? I have another example here where it says, we're dividing. We're going to divide two functions here. Okay. This has a little bit easier feel. You may remember this from before. We can't just take those two and divide. We're going to factor them. They factor. So like when you look at the top here, you may already see that this is an x minus 2 times an x minus 1. All right. I'm going to factor the denominator here. So I get 54, that's what, 9 times 6. So I get x plus 9 times x minus 6. When I divide two functions, that's the same as multiplying by the reciprocal of the second function. So what I'm going to do is when I factor these up here, I'm going to switch the top and bottom. So this is going to go on the top when I divide, and this is going to be on the bottom. All right. So if I do the top first, let's do the top first. This is, you may recognize it's a perfect square, x minus 6 times x minus 6. You could write x minus 6 squared if you want to, but I like keeping the terms separate as I simplify. The bottom simplifies to is at x plus 9 times x minus 1. Now I'm going to go through and cancel common terms. I'm going to guess common terms cancel. This x minus 6 cancels with an x minus 6. This x minus 1 cancels with an x minus 1. And those are all the terms that I can simplify. When I gather up my remaining terms, I get an x minus 2 on the top and an x minus 6 on the bottom. And then I have an x plus 9 squared on the bottom there. So that's going to be f of x over g of x. And that's it. So the test is, do you know how to simplify, and do you know when it's fully simplified? I see students still struggle of knowing, I'm done simplifying. That's all I need to simplify it to. That's it. All right. The other thing that we did with composition of functions is actual composite functions. We composed functions before, but it was basic mathematical functions. This is actual composite functions where we put one function into another. And you've been doing this also for a few functions before, our toolkit functions. So now we're looking specifically at rational functions. So I have a couple of examples here, example A and example B, for how to figure out the composite function, and also in here the domain. I see students still struggle with the domain at this point in time, so we're still going to review it. So then when we're working with composite functions, we need to be careful to limit the domain to the inside function first. So this is my inner function. G is my inner function. So what I know is that the domain is going to be limited to the domain of the limited function, as well as to the main function. All right. Oh, that was interesting. So what I'm going to say initially is x cannot equal 0 right away, because that's x in the denominator. X cannot equal 0. That's going to be one of my unallowed values. The next thing I'm going to do is identify my main function. So I'm going to take this function and put it in f. So 1 over 8 over x plus 9 minus 3. That's going to be f of g of x. All right, I'm going to simplify this. If I simplify it, let's see, I need an 8 over x plus 6. I don't want an x in the denominator, so I'm going to go through and multiply everything by a factor of x. So I'm going to get x in the numerator, and then I get 8 plus 6x in the denominator. And that's f of g of x. That's it. You may think that you need to simplify that more, but that's it. This is not the simplified term. Here, with the plus 6, 8 over x, you do not want a denominator and a denominator. You want to go through and multiply that through and get something that looks like that. Now we need to consider the domain of this function. So we don't care about the domain of the original outer function. We care about the domain of the original inner function, and we care about the domain of that final function. So the inner and the final, not the outer original one, okay? So we're going to say that 8 plus 6x cannot equal 0. 8 cannot equal negative 6x, and so x cannot equal negative, what is that, 4/3, divide by 2 everywhere. So that's our two domains limitations here, All right, so if I write out the domain for this, it's going to go from negative infinity all the way up to the next smaller number, which is actually the negative 4/3. I'm going to union it from negative 4/3 to 0, and then that'll be another union from 0 to infinity. All right, so those two values it can't be, and it can equal anything else otherwise. You can check the graph in order to make sure, verify your answer, but I am confident on that one. Let's do another example just to be clear. I know you have trouble with this, so repetition is good. So again, fully simplify, find the domain. So let's do this. And this one I did before, and I recognize where your algebraic error might be. This is a nice example. So first of all, we're going to identify the domain of the inner function, so g of x. This is our inner function. And what we're going to note is that x minus 6 cannot equal 0, so x cannot equal 6. So that gives us one of our points of our domain. I'm going to go ahead and calculate f, or simplify f of g of x. So I'm going to go 1 over x minus 6 minus 2. Okay? Don't start making up your own algebra rules here. You cannot just do the negative 6 and negative 2 together. One's in the numerator, one's in the denominator, and I need to make sure that all of them have the same denominator. I'm going to do the same trick as before. I had an x in the denominator, so I multiplied all the terms by x. I have an x minus 6 in the denominator, so I'm going to multiply all of the terms by x minus 6. 2x minus 6 down here, and then a 1x minus 6 on top. So I'm going to get an x minus 6 in the numerator. In the denominator, I'm going to get 1, right, because these two cancel. That leaves a 1. Minus 2x plus 12, yes? So f of g of x is x minus 6 over what? Negative 2x plus 13. Okay, so that gives us our other boundary condition here. We cannot have this term equal 0. Negative 2x plus 13 cannot equal 0. So when we're doing the domain, when you're doing the domain here, you have to find the domain of the inner function, which can't include x, and you have to do the domain of the final resultant composite function, which is given by that denominator not equaling 0. So x cannot equal 13/2. Okay, so when I write out the domain here in interval notation, because that's usually what they want, right? We're going to say that it can equal all terms except, let's see what's bigger, 6 or 6/2, 6. It can equal all values of x except these ones that I have identified. And then I'm going to just union all of these other regions that add up in between. Sorry, I'm talking and I'm writing at the same time, so I was having a hard time. Okay, so that's going to be our domain. We have our unallowed values of 6 and 13/2. And then it says, other than that, it can equal any other value of x. Okay, so that can be confusing, and I can feel you on that. Make sure you're executing your algebra and simplifying accurately. Don't be making up your own algebra rules. And then also check the domain of your inner function to combine it with the domain of the resultant composite function.